All right, in this example, we have a graph, and notice that the graph, here, let me highlight this. Notice that the graph is giving us f prime of x, right? It's f prime of x. It's not f of x, it's f prime of x. So this is telling us about the derivative. So the first question is, on what intervals is f increasing? Okay, now this is asking about f, not f prime. So, but when I look at this, the graph of the derivative is, notice it's above the x-axis, so f prime is greater than 0 until we get to 1. Sorry, less than 0. Again, is no, it's greater than 0. It's greater than 0. It's greater than 0, right? Because these values, I'm just looking at the values of f prime, and they're all above the x-axis, so it's greater than 0. Now it's still greater than 0 here, between 1 and 4, and then it's greater than 0, f prime is again greater than 0 until we get to 4, right? Okay, so it's greater than 0 for x less than 4, and the derivative is less than 0 after 4, right? When x is greater than 4. All right, so when is the function increasing? It's whenever the derivative is positive, and the derivative is positive for anything less than 4. So if we want to use interval notation, we're going to say negative infinity to 4. Okay, it's increasing. The original function f is increasing on that interval because the derivative is positive, right? And then the function is decreasing for anything greater than 4, so 4 to infinity. Okay, so again, I think this gets a little confusing because we're looking at the derivative here, right? These are values of the derivative, and we're trying to figure out what's going on with the original function. All right, and we're just looking at the sign of the derivative. So if these values are above the x-axis, they're positive, and so the original function is increasing if f prime is positive. All right, so at what value does f have a local minimum? All right, so notice, remember, critical points are when the derivative is 0, right? So the derivative is 0 here and here. So these are the critical points. Critical points, right? Now, if I were to draw a little number line down here and mark where those critical points are, oops, move that over just a hair, 4. We have the critical points at 1 and 4. We know that f of x is increasing and then continues to increase until we get to 4, and then the derivative is negative, so the function decreases. Okay, so you can see that we have a local maximum at 4, and it doesn't look like we're going to have any local minimum. Okay, so we have a local maximum at x equals 4, right? Because that's where our critical point is, and the derivative, the sign of the derivative, is going from positive to negative, right? So the original function is going from increasing to decreasing, and it doesn't look like we have a local minimum, right? So there's none. I'll just say none. Okay. Now we have another critical point, but it's neither. It's not a local minimum or maximum. It just the function, the original function, will increase until it gets to 1, flatten out a little bit, and then it'll continue to increase. All right, now it's asking about concavity, right? It's asking about the concavity of the original function f. Okay, all right. So now, because we have information about the derivative, then the second derivative is going to be determined by the slope of the derivative. Okay, so you can see, let me go back to this highlighter here. You can see that let's go to pink because I like that. So you can see that f prime is decreasing, right? So the slope of the derivative is negative, which means that the second derivative is negative for this portion of the curve because the slope of the derivative, right, is the second derivative. All right, and then if we look at the next portion of the curve, the slope of the derivative is positive, right? So when the slope of the derivative is positive, right, the slope of the derivative is the second derivative, that means that the original function is going to be concave up, right? And then again, let me switch to a different color again. This portion of the curve, it looks like the slope is negative, and so the slope of the derivative is negative, meaning the second derivative is negative. All right. So this is telling us the concavity. The slope of the first derivative is the second derivative. And so if the slope is negative, then the second derivative is negative. So where is f going to be concave up? Well, it's going to be concave up when the slope of the derivative is positive, right? So between 1 and 3 is where f, the original function f, is concave up, right? And then f is going to be concave down when the slope of the derivative is negative. So we have two intervals between minus infinity to 1. And we've got another interval. Let's put a union sign in here. And then from, looks like 3 to infinity. So we have two intervals where the slope of the derivative is negative. So the second derivative is negative, which means the original function f is concave down. All right, that's all I got for you today, and I'll see you in class.